In this lab, we are determining forces from motion observation using Newton's second law and Newton's universal law of gravitation. Given the position data for a star orbiting a black hole, I use the following steps to solve for the mass of the black hole. First, identify the system, the star in this case. Second, use observations to find Fnet, which is done using Newton's second law. Third, specify interactions. Fnet is equal to Fgrav since the black hole is the only source of a force on our system. And finally, use Newton's universal law of gravitation to solve for the unknown mass of the black hole, which is correctly found to be 3.5662 e to the 31st kilograms. The fundamental principles we use in the lab are Newton's second law in the form we know as the momentum principle. The derivation is shown here, and the final equation we use is Fnet equals dp over dt, as when delta t is small enough, which is assumed in this lab, derivatives can be taken, making Fnet equal to dp over dt. The other important equation in this lab is Newton's universal law of gravitation. The first part to calculating the mass of the black hole is calculating the value of Fnet. Analytically, this is done as shown here, moving from position data to Fnet. Once the net force has been calculated, Newton's universal law of gravitation can be used to solve for the mass of the black hole by plugging in the star's mass, delta t, the net force, and the gravitational constant. However, it is more convenient to let the computer do the computations for us. In Python, the initial conditions must be updated. The position of the black hole is set to the given location. The mass of the star is also given, as is delta t, and the program is set to read in the position data points from a CSV file. The first loop in the code is calculating the velocities. The code properly shows calculating the change in the x and y positions, as well as the x and y components of velocity. The next loop in the code is calculating the changes in velocity, which leads to the changes in momentum. This can only be done after the final and initial velocities and momentums have been defined, as shown here. The final part of the code is calculating the net force. Here the code is shown equating dp over dt to Fnet. dp over dt can also be broken into parallel and perpendicular components to better understand the motion, and the code for this is also included here. Running our program, we see that the star orbits around the black hole as we would expect. The program calculates the magnitude of the net force and the r vector needed for calculating the mass of the black hole, and these values are shown here. As seen when the program ran, different arrows break down the force. The net force arrow, the yellow arrow, points to the black hole since it is the only force acting on our system. Since the parallel components show speeding up or slowing down, it should point either in the direction of motion if speeding up, or opposite the direction of motion if slowing down. In other words, in either the positive or negative p-hat direction. And the final arrow, the blue arrow, is the perpendicular component, which shows curving. It should point to the center of the tangential or kissing circle, and this is also shown correctly. The final step for solving for the mass of the black hole is plugging in the values we have calculated previously into Newton's universal law of gravitation. Python calculated r in the magnitude of Fnet, and we are given the mass of the star and the value for g. Solving it out, we get that the mass of the black hole is 3.5662 e to the 31st kilograms. If a new black hole replaced the old one, but the observed motion remained the same, is it possible to calculate a different mass for the new black hole? Because we are moving from observations to net force, it is impossible to compute a new mass for a different black hole if the observed motion is the same. In order to predict a different mass for the black hole, at least one of the variables in Newton's universal law of gravitation must be different. With the observed motion being the same, we would calculate the same r and the same Fnet, and g and the mass of the star would already be the same, leading to the same mass for the new black hole. Newton's second law relates Fnet and delta t over delta t, proving that the values are equal, and this proof was shown earlier in the video. Because they are equal, the corresponding parallel and perpendicular components are also equal. Dimensional analysis of Fnet and dp over dt also proved to be the same, kilogram times mass over second squared. However, even though the values are the same, conceptually they mean different things. Fnet is the sum of all forces acting on the object, whereas delta p over delta t is a change in momentum. It is a cause and effect relationship. The net force acting on the object causes the change in momentum. This is seen in our lab when the change in momentum of the star is caused by the net force from the black hole. The change in momentum exists because there is a force acting on the star.